Welcome back to the Walking Clearwater Physics Textbook Podcast Series. I am your host VB Kataria, walking through Clearwater as we continue part 2 of Semiconductor Electronics, Materials, Devices, and Simple Circuits. In the last episode, I had made a mistake telling name in the starting, as you might have noticed from this episode and from the last, and I apologize for that, first of all. And moving on, in this episode, we'll cover everything from PN junction and its characteristics to diodes, rectifiers, transistors, amplifiers, and logic gates, the fundamentals on building blocks of modern electronics. So let's dive in, starting from 14.5 PN junction. A PN junction is the basic building block of many semiconductor devices like diodes, transistors, etc. A clear understanding of the junction behavior is important to analyze the working of other semiconductor devices. We will now try to understand how a junction is formed and how junction behaves under the influence of external applied voltages, also called bias. 14.5.1 PN junction formation. Consider a thin P-type silicon PSI semiconductor wafer. By adding precisely a small quantity of pentavalent impurity, part of the PSI wafer can be converted into NSI. There are several types by which a semiconductor can be formed. The wafer now contains P region and N region and metallurgical junction between P and N region. Two important processes occur during the formation of a PN junction: diffusion and drift. We know that in a N-type semiconductor, the concentration of electrons number from electrons per unit volume is compared to the concentration of holes. Similarly, in a p-type semiconductor, the concentration of holes is more than that of the concentration of electrons. During the formation of p-n junction and due to concentration of gradient across p and n sides, holes diffuse from p side to n side p to n, and electron diffuse from n side to p side n to p. This motion of charge carriers give rise to diffusion current across the junction. When an electron diffuses from N to P, it leaves behind an ionized donor on N side. This ionized donor positive charge is immobile as it is bonded to the surrounding atoms. As the electrons continue to diffuse from N to P, a layer of positive charge or positive space charge region on N side of the junction is developed. Similarly, when a hole diffuses from P to N due to the concentration gradient, it leaves behind an ionized acceptor, negative charge, which is immobile. As the holes continue to diffuse, a layer of negative charge or negative space charge region on the p side of the junction is developed. This space charge region on either side of the junction together is known as depletion region, as the electron and holes taking part in the initial movement across the junction depleted the region of its free charges. Figure 14.10. Figure 14.10 PN junction formation process. The thickness of depletion region is of the order of one-tenth of micrometer. Due to the positive space charge region on N side of junction and negative space charge region on P side of junction, an electric field directed from positive charge towards negative charge develops. Due to this field, an electron on P side of the junction moves to N side and hole on N side of the junction moves to P side. The motion of charge carriers due to electric field is called drift. Thus, a different drift current which is opposite in direction to diffusion current. Figure 14.10 starts. Initially, diffusion current is large and drift current is small. As the diffusion process continues, the space charge regions on either side of the junction extended, thus increasing the electric field strength and hence drift current. This process continues until the diffusion current equals the drift current. Thus, a PN junction is formed. In a PN junction, under equilibrium, there is no net current. The loss of electron from the N region and gain of electron by the P region causes a difference of potential across the junction of the two regions. The polarity of this potential is such as opposite further flow of carriers so that a condition of equilibrium exists. Figure 14.11 shows the PN junction at equilibrium and the potential across the junction. The N material has lost electrons and P material has acquired electrons. The N material is thus positive relative to the P material. Since this potential tends to prevent the movement of electron from N region into the P region, it is often called a barrier potential. Figure 14.11a, diode under equilibrium, V is equal to 0. B, barrier potential under no bias. 14.6 semiconductor diode. A semiconductor diode figure 14.12a is basically a PN junction with metallic contacts provided at ends for the application of an external voltage. It is two-terminal device. A PN junction diode is symbolically represented as shown in figure 14.12b. The direction of arrow indicates the conventional direction of current when the diode is under forward bias. The equilibrium barrier potential can be altered by applying an external voltage V across the diode. The situation of PN junction diode under equilibrium without bias is shown in figure 14.11a and b. Figure 14.12a semiconductor diode B symbol for PN junction diode. 14.6.1 PN junction diode under forward bias. When an external voltage V is applied across a semiconductor diode such that P side is connected to the positive terminal of the battery and N side is connected to the negative terminal. Figure 14.13a, it is said to be forward bias. The applied voltage mostly drops from the across the depletion region, and the voltage drop across the p side and n side of the junction is negligible. This is because resistance of depletion region, a region where there are no charges, is very high compared to the resistance of n side and p side. The direction of applied voltage V is opposite to the built-in potential V naught. As a result, the depletion layer width decreases and barrier height is reduced. The effective barrier height under forward bias V naught to V. If the applied voltage is small, the barrier potential will be reduced only slightly below the equilibrium value, and only a small number of carriers in the material, those that happen to be in the uppermost energy levels, will possess enough energy to cross the junction. So the current will be small. If we increase the applied voltage significantly, the barrier height will be reduced and more number of carriers will have required energy. Thus, the current increases. Due to applied voltage, electrons from N side cross the depletion region and reach P side, where there are many minority carriers. Similarly, holes from P side crosses the junction and then reach N side, where there are minority carriers. This process under forward bias is known as minority carrier injection. At junction boundary on each side, the minority carrier concentration increases significantly compared to the locations far from the junction. Due to this concentration gradient, the injected electrons on p side diffuse from the junction edge of p side to the other end of p side. Likewise, the injected holes on n side diffuse from the junction edge of n side to the other end of n side. Figure 14.14. This motion of charged carriers on either side gives rise to current. The total diode forward current is sum of hole diffusion current and conventional current due to electron diffusion. The magnitude of this current is usually in milliampere. 14.6.2 PN junction diode under reverse bias. When an external voltage V is applied across the diode such that N side is positive and P side is negative, it is said to be reverse biased. Figure 14.15a. The applied voltage mostly drops across the depletion region. The direction of applied voltage is same as the direction of barrier potential. As a result, the barrier height increases and depletion region widens due to the change in the electric field. The effective barrier height under reverse bias is V naught plus V. Figure 14.15b. This suppresses the flow of electrons from N to P and holes from P to N. Thus, diffusion current decreases enormously compared to the diode under forward bias. The electric field direction of the junction is such that if electrons on p side or holes on n side in their random motion come close to the junction, they will be swept into the majority zone. This drift of carriers give rise to current. The drift current is one of the order of a few microampere. This is quite low because it is due to the motion of carriers from the minority side to the majority side across their junction. The drift current is also there under forward bias, but it's negligible microampere when compared with current due to injected carriers, which is usually in milliampere. Then the diode reverse current is not very much dependent on the applied voltage. Even a small voltage is sufficient to sweep the minority carriers from one side of the junction to other side of the junction. The current is not limited by magnitude of the applied voltage, but it is limited due to the concentration of minority carrier on either side of the junction. The current under reverse bias is essentially voltage independent up to a critical reverse bias voltage known as breakdown voltage (VBR). When V is equal to VBR, the diode reverse current increases sharply. Even a slight increase in the bias voltage causes large change in the current. If the reverse current is not limited by an external circuit below the rated value specified by the manufacturer, the PN junction will get destroyed. Once it exceeds the rated value, the diode gets destroyed due to overheating. This can happen even for the diode under forward bias if the forward current exceeds the rated value. The circuit arrangement for studying the VI characteristic of diode, that is the i.e. the variation of current as function of applied voltage, are shown in figure 14.16a and b. Figure 14.16 experimental circuit arrangement for studying VI characteristics of a PN junction diode. A in forward bias, B in reverse bias, C typical VI characteristic of a silicon diode. The battery is connected to diode through a potentiometer or rheostat so that the applied voltage to the diode can be changed. For different values of voltages, the value of current is noted. A graph between V and I is obtained as in figure 14.16c. Note that in forward bias measurement, we use a milliammeter since the expected current is large. As explained in the earlier section, while a micrometer is used in reverse bias to measure the current. You can see in figure 14.14c that in forward bias the current first increases very slowly, almost negligibly, till the voltage across the diode crosses a certain value. After a characteristic voltage, the diode current increases significantly, exponentially, even for a very small value increase in the diode bias voltage. This voltage is called the threshold voltage or cut-in voltage. About 0.2 volt for germanium diode and about 0.7 volt for silicon diode. For the diode in reverse bias, the current is very small in micro amperes and almost remains constant with change in bias. It is called reverse saturation current. However, for special cases at very high reverse bias breakdown voltage, the current suddenly increases. This special action of diode is discussed later in section 14.8. The general purpose diode are not used beyond the reverse saturation current region. The above discussion shows the PN junction diode primarily allows the flow of current only in one direction, forward bias. The forward bias resistance is low as compared to reverse bias resistance. This property is used for rectification of AC voltages as discussed in the next section. For diodes, we define a quantity called dynamic resistances as the ratio of small change in voltage delta V to a small change in current delta I. RD is equal to delta V by delta I. 14.7 Application of junction diode as rectifier. From the VI characteristic of junction diode, we see that it allows current to pass only when it is forward biased. So if an alternating voltage is applied across the diode, the current flows only in that part of the cycle when the diode is forward biased. This property is used to rectify alternating voltages, and the circuit used for this purpose is called a rectifier. If an alternating voltage is applied across a diode in series with load, pulsating voltage will appear across the load only during half cycles of the AC input during which diode is forward biased. Such rectifier circuit as shown in figure 14.18 is called a half-wave rectifier. The secondary of a transformer supplies the desired AC voltage across terminals A and B. When the voltage at A is positive, the diode is forward biased and it conducts. When A is negative, the diode is reverse biased and it does not conduct. The reverse saturation current of diode is negligible and can be considered equal to zero for practical purposes. The reverse breakdown voltage of a diode must be sufficiently higher than the peak AC voltage at secondary of the transformer to protect the diode from reverse breakdown. Therefore, in the positive half cycle of AC, there is a current through the load resistor RL and we get an output voltage as shown in figure 14.18b, whereas there is no current in the negative half cycle. Figure 14.18a, half wave rectifier circuit. B, input AC voltage and output voltage wavefronts from the rectifier current. Thus, the output voltage, though still varying, is restricted to only one direction and is said to be rectified. Since the rectified output of the circuit is only for half of the input as AC wave, it is called the half wave rectifier. The circuit using two diodes shown in figure 14.19a gives the output rectified voltage corresponding to both positive as well as negative half of the cycle. Hence, it is known as full wave rectifier. Here, the P side of the two diodes are connected to ends of the secondary of transformer. The N side of the diode are connected together and output is known as output is taken between this common point of diodes and the midpoint of the secondary of the transformer. So for a full wave rectifier, the secondary of the transformer is provided with a center tapping and so it is called center tap transformer. As can be seen in figure 14.19c, the voltage rectified by each diode is only half the total secondary voltage. Each diode rectifies only for half the cycle, but the two do so for alternative cycles. Thus, the output between their common terminals and center tap of transformer becomes a full wave rectifier output. Note that there is another circuit of full wave rectifier which does not need a center tap transformer but needs four diodes. Suppose the input voltage to A with respect to center tap at any instant is positive. It is clear that at that instant voltage at B being out of phase will be negative as shown in figure 14.19b. So diode D1 gets forward biased and conducts while D2 being reverse biased is not conducting. Hence during this positive half cycle we get an output current and the output voltage across the load resistor RL as shown in figure 14.19c. In the course of an AC cycle, when the voltage at A becomes negative with respect to center tap, the voltage at B would be positive. In this part of the cycle, diode D1 would not conduct but D2 would, giving an output current and output voltage across RL during the negative half cycle of the input AC. Thus, we get output voltage during both the positive as well as the negative of the cycle. Obviously, this is more efficient circuit for getting rectified voltage or current than half-wave rectifier. The rectified voltage is in the form of pulses of the shape of half sinusoids. Though it is unidirectional, it does not have a steady value. To get steady DC output from the pulsating voltage, normally a capacitor is connected across the output terminals parallel to the load RL. One can also use an inductor in series with RL for the same purpose. Since these additional circuits appear to filter out the AC ripple and give a pure DC voltage, so they are called filters. Now we shall discuss the role of capacitor in filtering. When the voltage across the capacitor is rising, it gets charged. If there is no external load, it remains charged for to the peak voltage of rectified output. When there is a load, it gets discharged through the load and voltage across it begins to fall. In the next half cycle of rectified output, it again gets charged to peak value figure 14.20. The rate of fall of the voltage across the capacitor depends inversely upon product of capacitance C and effective resistance RL used in the circuit and is called the time constant. To make the time constant large, value of C should be large. So capacitor input filters use large capacitors. The output voltage obtained by using capacitor input filter is nearer to the peak voltage of rectified voltage. This type of filter is most widely used in power supplies. So that was the chapter. Now reading summary. 1. Semiconductors are basic materials used in the present solid-state electronic devices like diode, transistors, ICs, etc. 2. Lattice structure and atomic structure of constituent elements decide whether a particular material will be insulator, metal, or semiconductor. 3. Metals have low resistivity, varying from 10 raised to power minus 2 to 10 raised to power minus 8 ohm meter. Insulators have very high resistivity, greater than 10 raised to power 8 ohm per meter. While semiconductors have intermediate values of resistivity. Semiconductors are elemental, silicon, germanium, as well as compounds. Pure semiconductors are called intrinsic semiconductors. The presence of charge carriers, electrons, and holes in an intrinsic property is an intrinsic property of the materials, and these are obtained as a result of thermal excitation. The number of electrons is equal to the number of holes in intrinsic conductors. Holes are essentially electron vacancies with an effective positive charge. The number of charge carriers can be changed by doping of a suitable impurity in pure semiconductors. Such semiconductors are known as extrinsic semiconductors. These are of two types, n-type and p-type. 7. In n-type semiconductors, number of electrons much greater than number of holes, while in p-type semiconductors, number of holes greater than number of electrons. 8. In n-type semiconducting silicon or germanium is obtained by doping with pentavalent atoms like donors, while p-type while p-type silicon or germanium can be obtained by doping with trivalent atoms acceptors. 9. Ne into Nh is equal to Ni square in all cases. Further, the material possesses an overall charge neutrality. 10. There are two distinct band energies called valence band and conduction band, in which the electrons in a material lie. Valence band energies are low as compared to conduction band energies. All energy levels in valence band are filled, while energy levels in the conduction band may be fully empty or partially filled. The electrons in the conduction band are free to move in a solid and responsible for conductivity. The extent of conductivity depends upon the energy gap Eg between the top of valence band Ev and the bottom of conduction band Ec. The electrons from valence band can be excited by heat, light, or electrical energy to the conduction band and thus produce a change in current flowing in a semiconductor. 11. For insulators, Eg greater than 3 electron volt. For semiconductors, Eg is 0.2 electron volt to 3 electron volt, while for metals, Eg is almost equal to 0. 12. p-n junction is the key to all semiconductor devices. When such a junction is made, a depletion layer is formed consisting of immobile ion cores devoid of their electron or holes. This is responsible for a junction potential barrier. 13. By changing the external applied voltage, junction barriers can be changed. In forward bias, N side is connected to negative terminal of battery and P side is connected to the positive. The barrier is decreased while barrier increases in reverse bias. Hence, the forward bias is more. Forward bias current is more. It's measured in milliamperes, while it is very small in microamperes in PN junction diode. Reverse biased. 14. Diodes can be used for rectifying an AC voltage, restricting the AC voltage to one direction. With the help of capacitor or a suitable filter, a DC voltage can be obtained. So that was for the chapter. Now this semiconductor electronics chapter 14 is over, and the next chapter will be nuclei. So stay tuned and keep supporting the podcast. And thank you from my side. And thank you to all of my viewers and supporters.